Hey guys, welcome back to the series on PyTorch. Today we will be taking a deep dive into implementing convolution-like operations manually. So in short, we'll be looking at how convolution is actually implemented under the hood and how to implement a convolution-like operator if you ever want to. So when I say convolution-like, I mean operations that involve the sliding kernel over your input tensor. So what if you want to apply it manually? How would you go by? How would you go by doing it? You can always use for loops, but then if you want to do it in a more efficient manner, how would you do it? So PyTorch provides two utilities, an in functional fold and an in functional not unfold. TensorFlow, on the other hand, I don't think, as the last time I checked, it had no support for folding and unfolding. So in TensorFlow, I believe you will have to use for loops, but then I could be wrong. But PyTorch definitely has this ability. So let me go on to talk about how it's done. Right. So convolution, before I say anything else, is an expensive operation, right? Because I have to slide my kernel over the image and then compute operations. Now this is complicated and this is not the most efficient way of doing it. The reason being our hardware, the one that we use, it's more tuned for matrix operations, not convolutions. So matrix operations like matrix multiplication, vector addition, so these things can be done very efficiently. So if I can somehow cast the convolution operation as a matrix multiplication or a vector operation, that would make it more efficient. And that's what the fold and unfold operations do. And once you have it in a matrix format, you can use any of the lower level BLAS libraries or BLAS calls to be more quick about your operation. Right, so the first thing here is, let's see if give me a moment to enable my cursor. Right. So the first thing is, if you look uh, at this matrix above, so this is your original image. On the top right, this one is your original image. I have made it one channel for simplicity, and H and W are its height and width. Now, if I want to do a convolution operation on it, or any sliding window operation with a filter of 2 by 2 size, so the kernel is 2 by 2, how am I going to do it? So the first step is apply nn functional.unfold. What unfold operation does is it extracts all the blocks of the kernel. I mean, all the blocks that would correspond to a kernel. So when I place the kernel here, these four are my blocks, and then put them in a column, right? So there are four blocks, put them in a column. Now, then the kernel will move over here. It'll uncover these four blocks, and then finally it'll enclose these four blocks. Then when it'll go down this block, and finally these four blocks. So overall, we'll have 6 different blocks. And here you can see there are 6 different columns because this is basically some kind of fancy reshape operation where I take each block. Again, block is the area of operation for my kernel, and I put them in a column format. Um, so this is the middle figure. I can't see if my cursor is being captured, so I'm just going to call the figures top, down, top, middle, and bottom. Right. Now, um, well, it might have been a bit awkward when if you couldn't see my cursor before, so let me just double check. Oh, I guess you could see it, so not too shabby. Right, let's go back to what we were doing. Right, so now I have this matrix in this format, and each column corresponds to each block. Now I can perform any operation. I can do element-wise addition, subtraction, no matter what. So convolution here would be a dot product with a 4 by 1 vector. I apply whatever operation that I want to apply here, and then I fold it back. So nn functional fold takes it back to the format that you want. So here I want it back I want it to be packaged back as a 2 by 2. So it gets back packaged as a 3 by 4 matrix with 2 by 2 bits, 2 by 2 windows. So unfold and fold are just reshaping my data in a certain format for easy operation of convolution or anything that you want. All right. Um, okay, so let me first give you an example. Forget about the two bottom figures here. Let's start um, with an image with all ones here, and I am doing an unfold operation with a kernel of size 2 by 2. So if it's 2 by 2, there would be 6 columns because one window. Sorry, I had a slight tech issue, so I would have to jump back. So let me show you the 6 windows that we have. So this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So 6 windows for a 2 by 2 kernel, and that's why I have 6 columns. So the unfolding operation takes the 4 values from each window and then puts them in a column format. And then I can apply any operation that I want, and then I fold it back. So this unfolding operation is the same as im to call. I am the number 2 and then call image to column in MATLAB or any lower level library or any BLAST-like library. And fold operation would be call to im. Okay, so that's that. Um, right. So when I fold it, I again have to tell the algorithm that, hey, what size of kernels are we using? That means I'll take this column and then I'll put it in a 2 by 2 fashion, because when I take this, I have option of what is my kernel size, and I put it back and I get something. But now notice we didn't apply any operation here because I didn't want to, and the input and output are different. So let me show you how the output is computed. It's clear till this point because unfold operation is pretty straightforward, rearranging the data. But now when I fold my data and I tell it use 2 by 2 kernels, it'll take in the first column and then it will put it in this 2 by 2 fashion, right? So once I have this 2 by 2 fashion, then I can move to the next column, which means the next sliding window. Now the next sliding window would be here, right? So I will have this. So now I have to aggregate on the overlap bits. So I'll have 1, 2, 1, 1, 2, 1, and then I keep on doing it, and this is how I will retrieve these different values. So this is a very simple example that demonstrated the unfolding and folding operation. Okay, now I think we can jump to code, and I'd like to show you how to actually implement this in Python. And we will be using this simple example. And in this simple example, I will have an input which has a spatial extent of 6 by 6 and then has 3 channels. And then I will basically so I would implement convolution here. So convolution is I would be convolving by a 2 by 2 filter. Its input channels would be 3 because it's acting here, and its output channels are 2. So if you do the math, the final output would be 5 by 5 by 2. So pretty standard convolution. This is something that we will implement now. Okay, so we will be using two functions, the torch and functional fold and the unfold function. Now you can, let me just, well, okay, that's fine. Right, so these take in the input, the kernel size, the kind of dilatation, padding, and stride that you want. And you can learn more details about it, torch.nn.fold or .unfold, but it talks about how the values are computed. So this, yeah, that's pretty much it. But I think the example that I'll talk about will make it more clear. Okay, so let's begin. So let me first just import torch, and then let me define certain inputs. So the inputs that I'll define would be what I talked about in the slide. I'll I'll have just a bunch of ones, which batch dimension 1, channels 3, spatial with the following. And let me just put the one of the channels to be all twos. So just so that I can tell you how the channels align up as well. And let me also create the convolution kernel, which the output I want 2 channels, input has 3 channels, and the kernel size is 2 by 2. Okay, so I've created this. Let me show you what input is. It's a bunch of ones. The second channel is 2, and then 3. Hang on, let me resize my window. This is a bit too large. All right, this is good. Okay, so that's my input. Let me show you my weights. Again, just a bunch of ones with output channel 2 and the input channels 3. Good. Now let us basically apply the unfolding operation. So let me call it unfolded. So this is torch.nn.functional.unfold. And here I specify my input, and then I also need to specify the kernels. So since this is a 2 by 2 kernel I'll use, I want my columns to have 4 rows. Okay, and unfold it. And let me show you its size. Unfolded. Okay, so good. The first one represents the batch, which is fine. It's only one. The second one is 12. It's 12 because it is 2 times 2 times the 3 channels my input had. So 4, 4 3s are 12. And then the number of columns is how many times, how many values, how many blocks there are for my kernel to slide over. That's 25. Let me, just to make it easier, also show you how it looks like. So this is a bit too tricky. Let's just view one column. So let's view the first column. So you see first column has all 4s from the first channel, then 4 2s. So the way it's stacked is all the channels come together. So 4 blocks of the first channel, 4 blocks of the second channel, 4 blocks of the third channel. This is evident from the 2s. So that's why I put the 2 in there as a probe to show you how the ordering of things. And again, I mean, it's a row, but I said column, but row column you can use interchangeably because certain BLAS libraries are column major optimized, some are row major optimized. So that's a different whole topic. Great. Now, okay, now I have this unfolded bit. What I want is now we want to apply convolution, right? So what does convolution do? So for each 2 by 2 chunk, convolution will give me one number, right? In our case, it'll give us 2 numbers because the convolution filter, there are 2 channels in the filter. So it'll give us 2 numbers. I take all the 12 values from each block and I need to get 2 numbers for each, the 12 element block, right? So basically I need to multiply, so that's some sort of a matrix multiplication that's happening. So let me conv output. Let me type it out and then it might be easier to understand. And I believe I have this code is from the PyTorch help, but I don't remember. It's been a while, so just gonna copy from my notes. It will become clear when I explain. So it's not too complicated. I missed it. And then finally go back to the original transpose. Okay, let's see if it works. All right, so Let me show you. So the fact that there's a matmul here tells you I'm doing some sort of matrix multiplication. So let me show you what's happening. So first of all, let's see what am I made, what is A times B, what is B. So I basically cast my W matrix. This is not too useful. Let me do a shape. My weight matrix in a 12 by 2 format. Because what I've realized is, so the weight matrix has, what does the weight matrix need to do? It needs to take the 12 and then convert that into 2. Why 12? Because I have 3 channels and 2 by 2. So each block in my unfolded had 12 elements. So those 12 elements need to be cast into 2 elements as per convolution rules. So the 2 elements would be, because convolution has 2 output. So the weight matrix has 2 outputs, 2 output channels. Okay, so basically, um, in my convolution, 2 times 2 is 4, and 4 threes are 12. So all these, the last three, all of these elements act on each block. So I have put them in a vertical fashion, so as 12, and then the remaining two, the remaining dimension is the latter one. So it's transposed, right? And let's see what it is acted on. So it is it was a 12 by 2 matrix, and it will act on 1, 25, 12. Now, I've done nothing, just transposed the dimensions. The reason why I've transposed dimension is when you use matmul, it applies the matrix multiplication. So the common dimension should be the last dimension of the first matrix and the first dimension of the second matrix. So that's why I transpose 12 from the middle to the end, and then finally I transpose it back. Um, it's a bit tricky to understand. I urge you to try play around with it and mentally understand that what I'm doing is correct. So finally, my output, let me show you, is, well, choose a better name, 1 to 25, because so let me um, compare that with what we had as input. Okay, so my input, or the unfolded one, was 12 and then 25. And now my output became 225 because I've performed the convolution, right? And now, finally, all I need to do is unfold it back. So to unfold it, fold it back. I call fold. I give it what's my input, and then again, I need to specify what's my kernel size. And boom. Oh, sorry. So, okay, if you go to fold, I need to specify the input, the output size, and also the kernel. So I need to specify the output size. Right. So this is the input. My output would be 5 by 5. Why is it 5 by 5? Because if you do the math on a 6 by 6 image, a 2 by 2 kernel will give you a 5 by 5 with no padding. Yeah, we are not worrying about padding. So that's my output, and my kernel finally is 1 by 1. Why is it 1 by 1? Because convolution operation gives you just one number out, right? In our case, 2 numbers, but then those 2 correspond to, for each bucket, they are just channel values for each particular location. So that's why my kernel is just 1. Right, and then I'll do out.shape, and you can see it's 1, 2, 5, 5. So under the hood, I'm sure there are many more optimizations that are done, but at a base level, this is the kind of operation that under the hood happens. Or if you write libraries in CUDA internally, or cuDNN internally would do something like this to make convolution very efficient. And finally, I want to show you that this was indeed convolution. So we can compare the results of actual convolution and this. So let me actually perform convolution. So torch .nn .functional and convolution requires me the input and the layer, and then I'll basically subtract from the output that I got. All right, and finally we need to um, just we care about the difference. That's why absolute value, and then let me sum up all the differences, and you can see it is 0. So what we did was actually convolution. Now I started with a very simple integer-based starting point. Now, if you have doubles or if you have floating values in your input and your um, weight matrix, the values might differ because of floating point errors. But then the difference would be like of the order of 10 to the minus 10 or something, 6, 7, something like that. So there will be just floating point errors associated to it, if any, because of the way internally computation is done. But yeah, but this is basically what I wanted to get across is any convolution-like operation, you can cast it into matrix multiplication using the fold and unfold operations. And well, I personally had never had to use it, but then hey, if you were creating your own operator, you might just need to use it. So, all right, that is it for this video. I'll see you guys next time.